Hi folks, thanks to be here for this talk about Introduction to Stream Processing. I am Nicola Frankel. I've been working in software development for, 20 years in different positions, developers, architect, whatever. And since 2 years, I'm a developer advocate. Right now, I work for a company called Hazelcast, and Hazelcast has two products. The first one is an in-memory data grid. And you can think about an in-memory data grid as distributed data structures. So for example, if you have a hash map or a dictionary, whatever you want to call it in your language stack, then it sits on your memory. And the issue with that is at some point the memory of your node is limited. So Hazelcast allows you to distribute the data over different nodes of a cluster, so that you can grow horizontally to your heart's content. And of course, we don't only have hash maps, we have queues, stacks, whatever. We have a lot of different data structures. The second product that leverages IMDG is called Hazelcast Jet, and it does stream processing or data streaming. And since I will be talking about it later on, then I won't go further right now. This is our schedule. The first part will be dedicated to why do we do data streaming. There is very good reason, and I want us to be on the same ground here, because otherwise, I can show you cool stuff, but it would be useless. Then I will talk a bit about streaming approaches, and afterwards I will describe Hazelcast Jet. And because in the end I want to show you a demo, I will also talk about OpenData and the general transit feed specification. And finally, I will finish with the demo, which I hope you will find cool. So first, in a time before our time, when I started working at least, that all data was stored in SQL databases. There was no other choices. There were talks, or in academics, there were people talking about object-oriented databases. But in the industry, everybody used SQL databases. But even at the time, there were some issues with that. For example, we had use cases. They were not transactional. And basically, in that case, we needed to transform the data. For example, in analytics. So imagine you are a supermarket director and you want every hour to have the sales so you can prepare some last minute promotion for the next hour. Or your bank account, annual or monthly closing. You want your bank account to give you the balance. And those are specific use cases that are not really good within the bounds of a SQL server. And it boils down to this simple thing. When you are doing transactions, you are doing a lot of writes, and SQL in that case is a very good thing because it gives you constraints. So you cannot put bad data into your store. That the data you accept is constrained, so the only data that is in is of good quality, whatever that means. Like you cannot store anything. If you have a column that has, like a type int, you are sure it won't be a string because the SQL server will disallow that. And also you have those other constraints. So for example, you can have unique indices or this kind of stuff. And this is normalized data. But when you are reading and the analytics use cases or the reporting use cases that I mentioned before, you are only reading, you are not writing. So in that case, all those normal forms, they actually are hindering you. They are putting constraints on your reads and they are slowing down your performance. And so when you want to write, you want to be correct, but when you want to read, you want to be as fast as possible. And when your use case is only toward reading, of course, then SQL doesn't make a lot of sense. And yeah, SQL implies that basically you design your database with no duplication. So you have all your normal forms up to the third, you have your joins, and then you have your constraints. And yeah, when you join, again, you don't have duplicate. When you do your join, then it slows down your queries. The more joins you have, the slower it is. And so even at that time, we had need for these extract, transform, load processes, because you have different actors with different needs, and it doesn't stand to reason to use the same database. And another reason is that if you are doing a very huge analytics query, then probably the database will need to dedicate a part of its performance to answering the query, and then meanwhile the transactions, the normal stuff that you would do, would slow down. So it's not good. So we want to have different databases for different use cases. And in that case, you have a batch. And I believe that everybody has seen batches in his life. And basically the batch model extracts data from the main database, transform it in a way that is made to be easily readable, to be very performant toward the read. So you skip all the constraints and you can duplicate data. That's not an issue. And then you load it into your analytics or reporting databases. And yeah, batches, they are everywhere. I've done a lot of batches in my life. And again, I believe that you as well. And when you think about batches, they have two interesting properties. The first, they are scheduled at regular intervals. They can be daily, they can be weekly. Yesterday I talked with a friend and basically they have a batch that runs every 15 minutes. And then there is the time it needs to run. And when you design the batch, you make it so that basically the time it needs to run fits into the scheduling interval. So if you have a daily batch, then the batch must run under 24 hours so that at the next 24 hours, then it's ready. The previous batch has finished processing. And in general, it's the case. But at some point in the life of the batch, the data grows and grows and grows and grows and grows. And what was correct at the beginning of the batch inception might not be the case anymore. And again, I'm pretty sure that you have met batches that was either overlapping or very close to the next batch execution. And this is only the first problem. You can have other problems. For example, as I mentioned, you can do extract, transform, load. So basically you need to take all the data into memory to do your transform. And if your data is too big, then it's very hard to manage that huge amount of data and do the transformation in memory. And also, what happens if the batch fails during execution? In that case, even if the normal batch the next batch would run afterwards, then if you fail mid-execution, then you just add so much more delay that, again, you might be overlapping to the next batch execution. One of the easiest way to manage some of those issues is to keep a cursor. So basically, instead of loading everything into the memory, you just manage a small chunk and you keep a cursor and you say, oh, I have let's say thousands of records, but then I will manage the batch in chunks of 1,000. And then you keep the first 1,000 and then you manage it and then you execute your ETL. And then for the next execution, you keep the cursor and you start from this point on. Now you have other issue, because what about if new data comes in? How do you handle it? So it's a good workaround. You can go a bit further, especially if the batch fails. But if it fails midway through the first chunk, where did it fail already? Did it fail at the end of the chunk? How do you manage to restart the next batch with the chunk? Then you've got this interesting stuff is, okay, how do I manage the cursor? And for all those reasons came big data. So before it was the realm of SQL Server, and because there were use cases we were using SQL servers for that were not meant for SQL, came big data. One also of the reason is basically most, at least at the time, all of SQL Server, they were meant to be single nodes. Or at least they would say, hey, we have a primary node and then we have followers nodes. But it was very hard to do primary. So if the first primary node failed, then you could have those followers taking the lead, but basically you couldn't scale horizontally. The only scaling you could do was vertically, and as you know, vertical scaling is good up until a point because you reach hardware limit. And so big data came and say, okay, by design, we will have servers that basically we can parallelize everything. And if we can parallelize everything, then we can scale horizontally in an infinite way. The other thing that came with big data was this NoSQL trend. And the NoSQL trend also removed constraints on writes. But it's not a free lunch. You must understand that if you remove constraints on write, meaning that you have no trust in the data that is in your data store. Meaning that if you don't know in what form is the data in the data store, when you read the data, you must do a lot of checks to be sure that, hey, yeah, this conforms to what I'm expecting. So this is not a free lunch. You will be writing much faster. But basically, when you will be reading, either you trust blindly and there is a chance that is not null, that it doesn't conform to what you are expecting, or you must put a lot of checks in place when you read. This is called schema on read versus schema on write. The next step is taking the lessons we learned from event-driven programming. So you might have heard about the term event, and an event is just something that happens at a time. And if you have been doing GUI development using user interfaces, then you probably have done event-driven programming. In event-driven programming, you react to events that are sent by the user. When the user clicks a button, then you do something. When the user fills in the field, then you do something. And for a long time, this event-driven programming was limited to the realm of user interfaces. But now we can think about it like, why can't we make everything event-based? Why, when new data comes in, then we can't consider it as an event and react upon it? And if we start having this mindset, then we can see there is a lot of benefits. The first is it's memory friendly, because instead of taking the whole database to do the ETL or just even a chunk, then we just have a single slice, a single event. And this is much more memory friendly because, of course, this is much more limited in memory. Likewise, once you have a single event, then it's much more easily processed. And the final benefit is you've got now the push model versus a pull model. So instead of having a batch checking every hour or checking every 15 minutes, now every time there is new data coming in, you can do something. And basically, you are very close to real time. And so what I mentioned before, the fact that, for example, the analytics use case, you need to wait up until the hour to get the data. Now you get it as soon as it comes in. And the second benefit that you can see is basically you can see your events that come in. You can do whatever you want, and this is basically derived data. So it is in sync by default. Instead of having your primary database and your analytics database, and they are basically not in sync until the batch runs. As soon as you've got event-driven, then as soon as you got new data in your primary node and it's processed very fast because it's a single event, then basically your analytics database becomes much more closer to reality to the primary one, and you can think about your analytics database as derived data. And this opens a whole new world, because when you are doing batches, you are basically thinking about finite datasets, because it starts at like midnight and it ends at midnight minus whatever. But when you are going event-driven, then of course there is a beginning, but until you stop the process, there is no end. So this is an infinite dataset. And if you have been doing some programming already, you know that in some languages such as Java, there is a way to handle those infinite datasets. In Java, those are called streams. I believe in other languages there are other semantics for that, but this is exactly the same. So probably you already have this way of thinking. And of course, if you just have the stream, this is just an event, this is good, but it lacks a lot of features. So the next step is to have stateful streams. So basically, instead of handling event one by one, we can like aggregate events, so we can have aggregations, so as sums, average, or whatever. And even better, we can just not consider one event and all its other events afterwards, but we can consider a chunk in time. And this is windowing, and you can have like tumbling windowing or like sliding windowing, and you can do the same like averages or whatever over a period of time. And so basically streaming is smart extract, transform, load, because you will be reading from like a couple of data stores, and you will be, or not only data stores, you might also have events or like IoT devices, and then you will be producing the same. And meanwhile, you have this whole processing pipeline. And the good thing is you can combine them together, you can get more data to enrich them. And because this is made by design, you can distribute the load not only over all cores of a single machine, but over all nodes of a single network. And then you've got all your transforms that I mentioned before using like Java 8 streams, or let's say similar to Java 8 streams, and you're done. And now it opens a new realm, because now the analytics, for example, the sales director of the supermarket, he doesn't need to wait until the end of the hour or until the batch has run, so it will be after the end of the hour, to get insights. If you wait for the batch, so you need to wait, for example, for the batch, you need to wait up until the hour has passed, plus the time to run the batch. So let's say it takes 30 seconds. Then you can decide what to do to promotion, because your sales in that department were not so great. But the thing is, as I mentioned, this is finite data sets. Your mindset is framed in hours. But is that really relevant for the customer? Not really. What you want is you want to adjust your promotions according to your sales, even if they were like 5 minutes before the hour or 10 minutes before the hour. So by having events, you can react as soon as you've got data, and you can like do stuff that you couldn't do before. Like let's say, for example, in the last half an hour, I already have sold too much on, well, not too much, probably no salesperson would think about too much, but I already have like reached my objective in this department, but in this department I need to sell more. I will do the promotion just after 30 minutes because the customer doesn't care about waiting for an hour. And this goes for everything. And perhaps you have heard about this word. It was very popular like 10 years ago, complex event processing. Those were in the world of the enterprise, and you had an enterprise service bus where you could publish events and you could, let's say, aggregate or let's say compute some different events and to create a more insight into what would happen. And this was called CEP, complex event processing. But it was never very popular. Well, it was popular, the term was popular, but it was never really leveraged because, yeah, it was complex and it was hard to do this kind of stuff. But with stream processing, this is exactly the kind of stuff you can do because you can aggregate the events and you can have windows and you can process in however way you want, and you can add some business logic. Now this is good, but at some point you might want to handle the event. And basically there are two ways to do that. Either you do it on disk or you do it in memory. So those are two different approaches. For example, for persistent event storage, you've got Kafka, which is basically right now taking all the limelight. And there is also another one that you might want to keep note of called Pulsar. But because Kafka is very well known, I will just have a few words about Kafka. So also Kafka is distributed. It is on disk storage, which is a benefit. In that case, you are sure your events, they will be persisted on disk. On the other hand, it means that because you will be writing on disk and also like reading from disk, it's slower than in memory. And the good thing about Kafka compared to most previous technologies is that the consumer keeps track of the offset. So basically you can have a topic where you can read from, you can have multiple consumers, and the consumers are responsible for keeping the offset they are reading from. So you can have like very slow consumers and very fast consumers reading from the same topic, and it's not an issue. And I believe this is really a good stuff compared to previous technologies. On the other side of the spectrum, you have in-memory stream processing. So basically with in-memory stream processing, you don't persist anything, you get fast, but of course, if something happens to your nodes, you might lose some data. Of course, there are ways to still keep the data. For example, if you replicate the data along different nodes, then you must shut down all the nodes to lose the data. So the more nodes you have, then the better it is. So it's a trade-off between persisting and being a bit slower or being faster and running the risk. And you might have heard about Apache Flink. I mean, those are only some of them. Or of course, I will talk about Hazelcast Jet, but there are also cloud-based ones, just as Amazon Kinesis or Google PubSub. I like to just mention Apache Beam, because Apache Beam tries to be an abstraction over all those stream processing engines, because they more or less have the same design. They are just all meant to read from a source, do some transformation, filtering, whatever, and then write somewhere. So this Apache Beam project tries to be an abstraction over all of them, so you could use the Apache Beam API and just plug your own implementation. Of course, because there is no standard over stream processing yet, then it's a leaky abstraction. It might not be as easy as just removing one and putting another, but I think that this effort is worth mentioning. Now I have a couple of words about Hazelcast Jet. So first is it's an Apache 2 open source license, and by default it's a single drawer. So basically you can embed it in your Java application as a library, and then you will just start the Hazelcast instance from inside your application, and as soon as you distribute your application on multiple nodes, then all those instances will start to broadcast, and then they will recognize each other and they will form a cluster. And this is because we use Hazelcast MDG under the cover. The benefit of Hazelcast Jet also is you can start using the batch API, and because it fits your legacy model, and then you can evolve to a streaming model by just adding one line of code. And just mention, though we are open source, we also have a Hazelcast Jet Enterprise offering. Hazelcast Jet, and again, this is just an example because other stream processing engine, perhaps they don't use the same word, but they have the same concept. We have two concepts, the concept of pipeline and the concept of job. And basically the pipeline, it's a declarative way to declare where you will be reading from, your transformations, and where you will be writing to. And basically once you have done that, then you submit that to the stream processing engine. And the stream processing engine will read that pipeline, will distribute it all over the cluster, and by doing that, it will transform it into the job. So basically, a job is a running instance of a pipeline. As I mentioned, by default, the easiest way to run Jet is inside the Java application. You declare it as a dependency. So basically, it becomes a jar where you can use it. And then you start it using this new Jet instance, and they will form a cluster. Now, this is all well and good, but it has some downside. And the main downside is that in that case, your Java application and the Jet nodes, they must scale together. And this is not always what is desirable. And in general, in production, this is not what you want. So we have another way to deploy it. And basically is you deploy your Jet nodes independently from your application. And in that case, you don't embed, your application doesn't wrap the Jet jar, but just the Jet client jar. And then we've got deployments just in the form of Helm charts or Docker images, whatever you want. And then you can scale independently. And you've got an additional benefit in that case is you don't need to have a Java application. So we've got client APIs for Python, for Go, for C#, for Node.js, you name it. So you can leverage the power of Jet even if you are not running a Java application. So this is Hazelcast Jet, and as you can see, it's very similar to the previous diagram. Here we can see that we can read from Kafka, from IoT devices, from the file system, from database events. You might have heard the term about change data capture. This is exactly what we are doing. And if nothing fits your use case, we have an API where you can create your own reader. And on the other side, it's the exact same stuff. You can write a lot of different places. And again, if there is not what you want, you can create your own writer. I need to mention that regarding the enrichments, in general, your stream processing pipeline needs additional data. If every time you need additional data, you need to query the database for the same, or perhaps not the same data, then the benefit of running in memory just decreases because it will be time lost. In general, what you will do, and that's what I will be doing in the demo, is you will be reading at the beginning, you will be prefetching data that you know you will be needed from the database into the Hazelcast MDG. So this will also sit in memory. And because Hazelcast Jet will be able to access the Hazelcast IMDG. Everything fits into memory, so it will be much faster. This is just a view, so that I told you that Hazelcast Jet is able to distribute the load across all cores of a machine and across all nodes of a network. This is just a sum up. And of course, some operations might not be distributable. Then the API lets you say, hey, this operation cannot be distributed, so please keep it on this core or on this node. Now, when we have stream processing, it's fine, but we need some data. And of course, probably your company has a lot of data, but to have a demo, I want to talk to everybody. So I want to have data that everybody can access. And actually, there is some initiative called OpenData. And OpenData is to data what open source is for source code. And basically, it lets you access data in a free way. And I, from Europe, so I know about open data initiatives in Europe, but probably in your country, there are also some open data initiatives. So if you're interested, you can check in France, in Switzerland, or in the European Union. But it's not as easy as that. Basically, you've got some challenges. The first is how to access data. The second is the format. The third is there any standard? And the final is the correctness of the data. So regarding the access, as web developers, we would, as developers, not only web, we would expect data to be accessible through a web service. That is not always the case, and actually it's more the exception than the rule. Most of the open data that you've got, they let you download the file, which is not super fun, because then you need, every time you need to access the data, you need to download the latest file. The second problem is the format, because open data means open format or not. You will find a lot of places when they provide you with Excel or even PDF. It's not super easy to get data from an Excel or PDF. Finally, we have XML. Imagine we have XML. We are in the best situation, but then you know that if you are using XML, you probably will be using a grammar, so a XML schema or a DTD, and which one is used. So depending on the domain, on the business domain, you will need a shared standard, which basically you won't find. And you know this joke about, hey, if you are in a situation where you have 14 competing standards and you say, oh, I will create a standard to unite them all, then soon you have 15 competing standards. So it's also an issue. And finally, you might have heard about data scientists being unhappy that 80% of their time is done cleaning data. Well, this is, for example, from the demo, and this is an hour. And honestly, I have no clue what 25 hour is. So in that case, you need to be to make some assumption. Perhaps it's 1 hour the day after. You have no clue, or just ignore the data. My demo will be about public transportation in Switzerland. And for that, as I mentioned, I need a standard. So when I checked, there was this standard, the GTFS specification. And it's not a public specification, it's actually offered by Google, but at least it has the merit of being there. And you have two kinds of data. The first one is you have static data, and so basically you need to download files at the beginning. And here is just for reference, because there are a lot of them. And once you've downloaded them, now you need to have the dynamic data. And this is the GTFS proposed dynamic model. And as you can see, here is the root of the message. And then you've got this feed entity where you can have multiple ones. And then for every feed entity, you have vehicle position. So I just need to access that, and I'm very happy. So I go to something called the Swiss Public Transport website, and good stuff. They provide that in GTFS format. As I mentioned, static files that you need to download first as text file, and then you've got a dynamic REST endpoint. Everybody is happy. Let's start hacking. And this is what I got. And as you can see here, I don't have the vehicle position because that was an optional entity. What I have instead is a stop time update with a stop time event. And basically, I have every time to compute. So I first downloaded the file with the plan stop time, and it gives me an update about, hey, given this trip at this stop, I will be late by 1 minute. So every time I need to recompute the location, and then I need to basically check where I am from the trip. And this becomes my pipeline, and this is where the power of stream processing goes in. I will get the web service data, and I need to split it into the different trip updates. Then I will get data from the trip itself, then from the stop times, because my front-end developers wanting to work with timestamp and not hours, I need to transform them into timestamp. And then finally, I enrich everything with location data. Then I send everything to AMDG, and it gives me the following architecture. Before running the demo, I need to get hold of the file, and then I have one job for each file, so that I will be loading the reference from those files here, and I will be sending them to IMDG so that the enrichment, as I mentioned, will be done in memory. Then, when I'm ready, I will run the second job, which will query the OpenData endpoint. It will enrich using what already sits in IMDG, and I will store the enriched data in a new map. And then I have a Spring Boot web application. It can be anything, but here, because I will be coding everything in Java and Kotlin, it will read the changes from this IMDG, and it will display all the points on the map. And now it's time for some demo. Now I'm inside my IDE. I will, as I mentioned, I will be using Kotlin, but you can work with your own stuff. And the first thing that I need to do is actually get the data file. Of course, they are prepared here. I've got them. So I will run a local jet instance. And then I will read the static data. So here you can see that I added some logs. You can see that it's reading the data file, and this is a job, for example. So here you can see the core code, and basically here I have my main function, so it will execute on a new jet client. It will execute those jobs one at a time. And here you have those pipelines. So let's see the stop one, which is the easiest one to understand. So I've created a shared pipeline function. And what it does, basically, it will take the name, it will take a function that takes a list of string and transform it into a JSON object, so that in the end, I will be able to enrich it using JSON API. And basically, it reads from the file, it applies some cleanup. So for example, I remove the first line, and afterwards, it JSONify it. And in some cases, I will try to do some merging, but otherwise I will just pick, which basically is the reason why you see that in the log. Then I transform it into a map entry, So I will take the ID as the key and the JSON as the value, and I write it in its dedicated IMAP. So I will have a map for each file that you see here. And it's taking a bit of time, so let's do some fast forward. So time has passed, and now my job has finished. It took a bit of time, as I mentioned, but now everything from those files is in memory, each in their dedicated map. Now the next step is to actually call the endpoint. And for that, I have another module, which has another pipeline. And if you remember the slide that I showed you, this is exactly the process. I will read from the endpoint, I will split the payload, I will enrich the trips, I will enrich the stop times, I will change it to timestamp, and then I will enrich with the stop. And at the end, I will write everything into a dedicated map. So let's do it. I will launch this job. And here I have additional log, again, because this is I picked. And now the final step is to start the web application. So let's launch it. You can run it in debug, but it doesn't change a thing. So the web application has started, and let's go to the browser. And here it starts. So you can see that on the browser side, I have started a WebSocket registration. And so I'm reading from the web application that reads itself from the IMDG, puts it into a queue, and then I'm sending this queue to the front end. And here you can see that it's starting to read from the queue. So every data point here is an element from the queue. And then I'm interpolating between the planned stop and the stop that I computed. And you can see that at some point they will start moving. So here you can see they start moving already, but because I have a lot of data points, and of course it's a bit power hungry regarding the memory and the CPU. So red means it's a train and green means it's a bus. And here you can see its name, its company, and that right now it's between Enge in Simmental and Boltingen, and soon it will reach Boltingen. So I believe this is an interesting demo, and you can of course do it at home. So as a recap, we saw where we came from batching, and how we can leverage streaming to get data as soon as it is emitted. And with streaming, we can leverage OpenData, but be careful because it's the Wild West, so there are no standards, and the real world data is not of super huge quality, so you need to create it a lot. But if you find the right OpenData, then you can get very cool stuff down. So thanks a lot for your attention. You can read my blog, you can follow me on Twitter, you can read more about Jet on this website, you can read more about the GTFS specification here on this website, and to get the demo at home, you get this GitHub repository, and I hope that the README is complete enough so you can start doing it.